that fundamental theorem of calculus as it applies to our definite integrals. It was telling us if we're integrating from a to b of f of x dx, then that would be capital F of b minus capital F of a. So let's look at some of the types of questions they're going to ask you on the multiple choice questions that will look like this. So let f be a differentiable function such that f of 3 equals 2.345, f prime of x equals the natural log of x squared plus 1. What is the value of f of 5? Okay, so they've given us f of 3, and they want f of 5, but the equation they gave us was f prime. So we cannot figure out f of 5 using f prime just directly, right? We can't just plug 5 in. That's not going to work. So the way that we're going to have to approach this, if we integrate f prime of x from 3 to 5, the fundamental theorem of calculus tells us that when we integrate this, when we integrate f prime, we would get f, and we would do f of 5 minus f of 3. Okay, that's just applying that rule there. I chose 3 and 5 because I know what f of 3 is, and I'm being asked what f of 5 is. So that's why I chose those as my lower and upper limits. So we can do this part right here on the calculator because they did give us the equation for f prime. So to integrate, do a definite integral on the calculator. Pay close attention. You probably want to try on your own to do this as well. So on the calculator, you're going to go to F3, which is calculate, and you're going to pick number 2, which is integrate. Okay, so F3, and you're going to pick number 2, which is integrate. Get the integral symbol here. You're going to type in your equation for your function, or if you wanted to, you could put it in y1 and use y1, but we'll just do this here. So we're going to do natural log of x squared plus 1. All right, so you type in your equation. You're going to tell it comma x, comma 3, comma 5, and close your parentheses. So your comma's there at the end. You'll type in your equation. You got to do comma x to tell it which variable it's doing this in terms of, comma 3 for your lower limit, comma 5 for your upper limit, and then you'll close the parentheses. And you probably want to hit the green button before you hit enter, or it might give you crazy stuff. I'm not sure if it'll give you this one or not. So this value this right here is going to give us 5.63144. That will equal f of 5 minus f of 3. But we know what f of 3 is. F of 3 equals 2.345. Okay. Questions there? Yes. Hit the green button and then hit enter.
You have to press the
Okay. So next time, hit the green button before you hit enter, and it should, or the green button before you hit enter, and it should give you the decimal. And if you do that on your calculator and it's giving you like a bunch of tangents and crazy stuff or whatever you're getting, go back and do it again and hit the green button and hit enter. Because, like, on the AP exam, if it's free response, they will accept it if you write down all of that stuff. But there's a good chance that you're going to make a mistake writing down all that stuff. So it's much better to use the decimal because it's much less likely that you'll make a mistake. So they will accept it if you just write down all of that stuff there. Okay. Now, the question asks us for f of 5. So all we got to do is solve this for f of 5. So we're just going to add 2.345. And so I think we should get 7.97644, which is going to be answer choice D here. Okay, questions? All right, let's look at the next one. Okay, so selected values of the twice differentiable function f and its derivative f prime are given in the table above. What is the value of the integral of f prime of x dx integrated from 0 to 3? So when we integrate f prime, we would get f, right? So I'm going to write this step just because we're going to do this later. So when we integrate f prime, we get f from 0 to 3, which is a step you don't have to write. And so to evaluate that, you would do f of 3 minus f of 0. Those values can be found on your table. F of 3 would be 10. F of 0 is 4. So we should get 6.
That was too simple. You knew that because the integral and the derivative cancel out.
Correct. Right. So,
when it is separated.
Right.
When they cancel out, it's just
Yes. Yeah. So integrating something is going to go like back up. Usually we're like function, first derivative, second derivative. If we integrate, it takes us back up to the one before it. So where we're integrating f prime, it takes us back up to the function above it, which would just be the f. Okay? Questions? All right, I like this one. I think it is pretty simple once you got that idea. And you'll see something like this because it's really important that they're testing that you understand the relationship between the f prime and the f there. It is, but when you integrate it, because you're doing the integral right here, then when you integrate it, it's going to give you f. So integrating the derivative takes you back to the original function. And then you plug into that function. Does that make sense? And they give you this, like you don't need this line right here at all, but they give it to you trying to confuse you so that you will do like 6 minus 5 there. Use the wrong line on that one. Because whenever you integrate f prime, you will get f. Right? So if you just did like f prime of 3 minus f prime of 0, you wouldn't be integrating anything because you didn't change anything. You're just plugging 3's and 0's in. So to integrate means that you're integrating whatever you've got here. So that, I mean, we're going to learn today how to do that with different functions. But right now we just know, normally you would have f of x, and then you get f prime of x, and if you took the derivative, you get f double prime of x, and that'd go on, right? So if we are integrating to take a derivative, it just goes down that line. If we integrate, it takes you back up that line. So when we integrate the f prime, it gives us f. It is always going to be there. It tells you what variable you are integrating with respect to. For pretty much everything we're going to do, it should always match. Right here, when we get to like some chain rule, U substitution stuff, it'll be important that it's there. Right now, it's kind of like when you're typing in the calculator, you put that comma x and then the comma 0, comma 3. It's just telling us what variable we're integrating with respect to. So that's just what the rule tells us to do. We always subtract. If you think about position, too, like when we were integrating velocity, it was our change in position. So you would take position at 3 minus position at 0 to see how far the particle was displaced.
Those are the rules that we had on the homework.
Yeah.
So we need to memorize those, or like on a note card? Is that what we?
This is different than the note card stuff. Note card stuff was like your sigma notation. All of this stuff you'll have to know. You won't have a note card. You on the actual AP exam, you won't have a note card for sigma stuff either, but we're just getting that is good enough. Okay. All right. So for number 6, we've got g of 4 equals 0.325. G prime is this complicated equation, and we want to know the value of g of 1. So this is similar to the one we did a couple problems ago. I need to integrate g prime of x. What should I use as my limits? 1 and 4. Because I know what 4 is, and I need to know what 1 is. Right? So if I integrated this to integrate g prime, I would get g. So this would be g of 4 minus g of 1. So everybody do that on your own calculator. I want to make sure you guys can do that part on your calculator on your own. Luis, do you know where yours is at? Just make sure you know where it's at. Don't be like Morgan Wiles, who had to pay $150 for her so that she could graduate. Not the Morgan Wiles that's here now. Yeah. But there was another Morgan Wiles. And she was a genius and made a 5 on the AP exam and super duper smart, but she could. I'm not sure if she was one of those or not. Is that negative? But she lost hers, which is not surprising. She should have won the math award that year because she was the smartest one in the class, but she did not because she didn't have her homework half the time because she couldn't find it in her book bag. But she made a 5 on the exam. She was super smart. Yes, it does. You want to put the bottom one first and the top one last. If you put them backwards, you'll get the wrong sign on your answer. This is one I actually would probably put it in y equals because it's such a complicated equation with so many parentheses that if you try to put the equation into the integral along with all the parentheses you got to have for the integral, so I would probably do it in y1. didn't hit the green button.
I didn't either.
Oh, good. It gave me a decimal anyway. Sometimes it will give you a decimal anyway. All right, I got 2.15572. Argument error does not sound good. When you type in y1, you got to do parentheses x. So it's going to be like y1 of x. Not right there. Go back beside the 1 and then do parentheses x. Like open parentheses. Yeah. And then do an x and then close the parentheses. So it's like sort of like f of x notation. Right? Like for g of x, you're going to y1 of x. And I think it should work now. Very good. Alright, did everybody else get theirs to work? Yes, that should be fine. I think you're typing everything in right. Addison's calculator is possessed. Okay. All right. Okay. All right. So you'll just plug in your numbers here. Daniel, be nice to people. All right, so we take that number, subtract our 0.325, and we'll get negative 0.1094 equals negative g of 1, and divide off our negatives, so you'll get A as your answer there. Like 5 or 10 minutes, I think. Okay, so if we had gotten far enough, I would have given you these last 3 along with your homework, but we didn't get far enough, so I want you to try them right now, okay? So try those right now. All right, so we've already talked about this a little bit. If we're looking for a function whose derivative is f of x equals 5x to the 4th, we could use, I'm going to use the capital X. So since this doesn't have a prime on it, so like if we're thinking about, like if we have f of x, if we take its derivative, we'd get f prime of x. If we take its derivative, we'd get f double prime of x. To go backwards, you're integrating. So if you've got to go from lowercase f and you need to integrate, there's no primes to take away here. So we usually use a capital f of x to show that that's the integral of our lowercase f. So I'm going to use a capital F here, and so the derivative of if you went back another one, then So they're probably not going to ask you to integrate when they've already used the capital F. So maybe you could do a really big capital F. I don't know if you had they will. Anything on AP exam for sure will not ask you to integrate something that's already your capital F. So capital F, if we integrate this, we would add 1 to our exponent, and then we divide out front by that exponent, which 5 divided by 5 would just give us a 1. So this function has a derivative of 5x to the 4th. But as we were talking about earlier, it's not the only function that would work. We could also use x to the 5th plus 7. Or x to the 5th minus 10. Or, as a very general form, what we're going to use is a capital C. So f of x, x to the 5th plus c. In text, whenever it's typed, you can usually tell a difference just based on how it is. They're not going to make a big deal whether you use a lowercase c or uppercase c as far as grading anything. So this c here is the letter we use to represent a constant in integration problems. And you must always, 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 when you're just doing general integrals, this is called infinite integration, because that c could be any number, which means you have an infinite number of solutions, right? So you always have to put that plus c when you integrate for these types of problems.
Why do we not put
So you are putting c that could be any number. It could be 1, it could be 7, it could be 1,000,000. Infinity is the largest possible number. It does not include all numbers. It is the largest possible number. So
I thought that it was just everything in between. I didn't know it was.
it is. If you could, I mean, like, 1,000,000 is a big number. If you add another 0, it's bigger. If you add another 0, it's bigger. So if you could add zeros forever until you reach the very highest possible, then you would have infinity. But you can't, because you can always add another 0 to your number. So it's just a theory. You can't actually get there. Yeah, if you spend the rest of your life adding an extra 0 onto 1,000,000, yeah, somebody else, and then pass it off to your children and continue this forever, you'll still never get there. What's that?
By choice, I bet.
Yeah. She probably is soaking it in. She just doesn't have the ability to communicate. Yeah. Whenever Hunter was like 6 months old, Todd was giving him a bath and yelled for me to come up there to look, because he had these like bath crayons. And Todd was like integrating things on the bathtub and told me that Hunter had done it at 6 months old. He had done it correctly. Uh-huh. It's Todd. He likes here, Ethan doesn't know. Here. This capital F is, sometimes we call it the integral. We can also call it the antiderivative on an interval I if capital F prime of x equals f of x. This is just saying that capital F is the integral of lowercase f here. So I kind of already explained that. So we did for homework, don't worry about it too much. All right. So we did for homework, the general rule for this. Oh wait, is that one? Hold on just a second. Hold on. I thought, I may not be meaning to put here what I was going to put there. So let me just look at the completed notes really quick and make sure. Normally I have the notebook here to look at what I'm supposed to write down, but there's two things I'm thinking of that could go here. Okay. Good. I'm glad I looked at that because I was going to tell you the wrong thing. Okay, so some notation that we have looked at before. Another way that we have said the derivative is we've called it dy dx. So if we have something like dy dx equals, I'm going to call it f of x. So you guys were asking about that dx notation. So one thing that I'm going to show you here, if I multiply both sides by the dx right here, it's going to cancel. On the left-hand side. And then if I integrate this here on both sides, when I integrate dy, I'm going to get y. And over here, if I'm integrating lowercase f, I would get capital F of x. And then we always put the plus c there on the end.
So what does this mean? Does this mean anything?
So, the dx here is telling you the variable that you are integrating with respect to. So like in the calculator, when you type it in, you have to type in your equation, then you put the comma x, right? So that dx is a lot like having that comma x there, letting us know that that's our variable that we're integrating with respect to. It's not mathematically correct to say this, but it will help you remember. You can think of it like dx, when you integrate, gets replaced with the plus c. Technically, mathematically, that's not what's happening, but if you think of it like that, you'll get the answer right for that.
So you're allowed to add that dx type derivative to both sides?
Yes.
So you just like add it yourself because you know.
What you're doing there, we'll talk about it more when we get to differential equations, but you're separating your variables. So you're getting all of your x's on one side and all of your y's on the other. Because otherwise, if you like tried to integrate both sides, you couldn't have an x and a y on one side while you're integrating. So that's the reason that we would move that over to the other side. Okay, so let's just look at the problems that we're going to see. Find the antiderivative, capital F of x, for each function. So if we're integrating here, what do we get when we integrate just 8? Not 0, that's the derivative. 8x. Plus c. Don't forget your plus c. So a way to think of that is it's like it's got an x to 0 power there, so you're raising that exponent 1, which gives you x to the first. Dividing out front by 1, you get 8x.
So that means 2 is just c.
Okay? For 2, you could think of it like you got x to 0 here, but even if you raise that to the first power, you still have a 0 out front, right? So 0, when you integrate it, you're not going to get anything for that. You're still going to get 0 whenever you integrate it. But you do have to put the plus c. So it'll just be capital F of x. That should be an equal sign, not a plus there. Equals that c. All right. Let's see, Emerson, what will we get whenever we integrate number 3? Plus. All right, remember, see, and Emerson's doing what's going to mess us up. This should be easy, but he integrated the 10x. What was he doing to the 3? He said 0. He was taking the derivative. So what happens from this point forward is sometimes I ask you for the derivative and you integrate, or I ask you to integrate and you take the derivative because we just get it all jumbled up. So be really careful with that. So when we integrate 3, we're just going to get 3x, and then we put a plus c on the end. It's always like after this point, I start seeing students mess up on like really basic derivatives. And it's because they start integrating instead of taking the derivative here. All right, let's see. Daniel, what will we get for number 4?
That's x to the 4th minus 3x squared plus 2x.
Okay, looks great. All right, Thomas, what about number 5? Since you don't like them. Did I turn the quarter back on? Yeah. Uh-huh.
X to the 5th minus 9x to the 3rd plus 10x plus c.
Plus C. Good.
That
Wonderful.
was a hard multiplication.
All right. Okay. Now, I've got a fraction here. Let's move it up. So I'm going to move this up and make it a negative exponent. All right. Luis is not afraid. Luis, what did you get? Okay, does that look good? Yeah, that's good. All right, so when you have fractions like that, if you can, you're going to move those up to the top to make them negative exponents.
We have to simplify that and put the thing back on the bottom.
Sometimes they will do that, but like if it's for response, it doesn't matter. Yeah. All right. Okay, so just some quick rules. These should be on there for you. If you integrate 0, you're just going to get c. If you integrate a constant, you're going to get kx plus c. So whatever the constant is times x plus c. If you integrate two functions that are added or subtracted, you can just integrate them separately. And then here we just have our opposite of our power rule, which is what we did on that worksheet last night. So now you're going to see some, I believe, on your homework to ask you to solve each differential equation for y. Now we will do an entire chapter on differential equations, but this is the very most basic type of differential equation that you will see. So for these differential equations, it's like the notation I was just showing you. You would want to multiply both sides by dx. And that gets all of the y's on one side and all of the x's on the other side.
What's the D stand for?
Derivative. So you would integrate both sides here. When you integrate dy, you just get y, because it's like integrating 1. And to integrate 1 with respect to y, you would just get a y. You technically could put a plus c on this side. But we're not going to, because, actually, I am going to, but I'm going to let you know we don't have to. Okay. I'm going to tell you what, we will never do this again after this one particular time. I'm just going to explain to you why we don't have to do the c on both sides. So we integrate 5x, which is going to give us 5/2 x squared. And we're going to put a plus c over here. And actually, I'm going to call this c sub 1 and c sub 2 since I've got two of them. C represents an unknown number, right? So if C1 and C2 are both unknown numbers, if I move this C1 over here, it is. I think it is recording. Yeah. This thing goes away for some reason that makes me nervous, but it is recording. So if I subtracted that C over there, an unknown number minus another unknown number, it's still an unknown number, right? So I could just call it a single plus C. So we're not going to ever do that again where we add both C's to both sides, because we can just add it to one side and it's like they've been combined, right? So we won't do that again where we put it on both sides. We'll just add it on the one side. Okay, questions on 7? For 8, we would multiply by dx. Whenever you multiply by dx over here, put some parentheses. So you've got dy equals 8x cubed plus 9x squared minus 4 dx. And you would just integrate both sides. You can see, essentially, it's just asking you to integrate whenever it's giving you a problem like this. So, Noah, what would we get whenever we integrate this one? Oh, it's beautiful.
Do you have to put the y?
I can live with it if you don't show this step right here on these problems. So if you just go straight to integrating, that's fine. When we actually start doing differential equations that are more difficult, it'll be important for us to separate those variables out first. But for these, if you don't, because they're such simple problems, it's fine. Okay. All right. Here's our last ones. So, Margaret, what would we get whenever we integrate number 9? It doesn't matter. If you like to have them in order, it's fine. Perfect. Well, almost perfect. Whatever. Let's see. Okay, number 10, I've got a square root. I need to think of this as x to the 1/2 dx before I integrate. So whenever I do that, Eli, what will I get when I integrate that one? Or tell me how to do it. I would probably write out another step on this one. What do we do first to our exponent? And that'll give us 3 over 2. Then I have to divide out front by that 3 over 2. Right? So dividing fractions is easy as pie. Flip the second and multiply. So I got 1 times 2 over 3. So it just ends up being 2/3 x to the 3/2 plus c. Number 11. I need to make this negative exponents before I try to deal with it. So x to the -4 dx. Selena, what will we get whenever we integrate that one?
I have x to the -1/3, -1, -3, sorry.
Okay.
And then I thought you would have to do like 1/3 and then you multiply it out to 1.
Very. I think that'll work. Yeah, because when you multiply it out, -1/3 times -3 would give you the +1, and then you just decrease your exponent by 1 would give you -4. So that works fine. Plus c there. They might move that 3 back down to the denominator. There, it's fine. All right, any ideas on what to do for number 12?
gotta do that.
What? Okay. So if I do that, it'll look like this. X to the negative 1/2. X times x plus 5 dx. We don't know a product rule for this. Distribute. So you get, what do you get when you multiply x to the negative 1/2 times x to the first? X to the 1/2. You add the exponents. So negative 1/2 plus 1 would give you 1/2. And then you would do 5 times x to the negative 1/2. And I'm running out of room. There's dx over here.
On the right side of that, like just everything. That's just
So that's what I did here with this x to the negative 1/2. And then you have to distribute it. Because if you have two things that are multiplied, like you would have to use a product rule if you're doing that, you cannot, we don't know how to do that yet. Or we're not going to learn how to do that, actually. So this is how we do it. The other option, the other way to think about this is think about doing that love connection. Right? You could do x divided by x to the 1/2 and 5 divided by x to the 1/2, and that'd give you the same thing here. So if we integrate this, Chandler, what are we going to get when we integrate? Yes. 2/3 x to the 3/2, which is basically what we did right here, right? All right, plus 10x to the 1/2 plus c. Now, if you need an extra step there, we got 3/2, and it was 1 divided by 3/2 here for that first one. And then for the second one, whenever you add 1 to the negative 1/2, you get a 1/2. And then you got it's 5 divided by the 1/2. 5 divided by 1/2 is 10 plus c on the end. It's going to give you this here. Okay, questions? All right, I want everybody to try to do at least the first 5 problems.
Those are odd, right? That's it?
No, you're doing all of them, 1 through 22. But these should be fast. This is like power rule. It should be ones that you can do pretty quickly.